Good day everyone. Welcome to the lecture series on power electronics. In this session we shall discuss three-phase semi-converter operation with continuous load current. Three-phase semi-converter circuit diagram is shown in this particular slide. You can see that input side we have three-phase balanced supply, and output side so I have considered a load, RLE load. It has 3 thyristors and 4 diodes, where one of them is a freewheeling diode, so which will allow freewheeling path for current to flow. And role of this freewheeling diode is to make sure that there is no negative voltage appear across the load. Okay, and there are 3 arms, each corresponding to one phase. So A phase is connected to one arm, so in which T1 and D1 are present, and B phase arm, so T2 and D2 are present, and C phase arm we have T3 and D3. And this T1, T2, T3 are in common cathode mode. They are connected in common cathode configuration, where these diodes D1, D2, D3, so they are connected in common anode configuration. And these top thyristors T1, T2 and T3, they belongs to positive group, where D1, D2, so D1, D2 and D3, so they belong to negative group. Right? Now let us consider the three-phase supply voltage and three-phase balance supply voltage. A phase voltage, B phase voltage, C phase voltage are shown in this particular graph. They are equal in magnitude and 120 degrees apart from each other. They are balanced. Coming to conduction diagram, so T1, T2, T3, so naturally they are going to be forward biased at this instant, that is at pi by 6 and 5 pi by 6 and 9 pi by 6 respectively. Okay. Usually thyristors are forward biased whenever their voltage is more than other two phase voltages. And to start with, I will consider alpha is equal to 0. So for alpha is equal to 0, T1 would be triggered at this instant, and for this 120 degrees, so T1 is going to conducting, and at this instant, that is at pi by 6, T2 is triggered, and that would conduct for next 120 degrees. And at this instant, that is at 9 pi by 6, T3 would be driven in, that is going to be fired, and that would conduct for next 120 degrees. So this is the conduction period of each thyristor for alpha is equal to 0. So coming to diodes, they do not require any firing, any gate current. Once they are forward biased, automatically they would conduct. And they are in common anode configuration. Diode with less or more negative voltage would be conducting. Now D3 would be D3, that is in C phase, would be in conduction mode from this instant onwards, that is at pi by 2. From pi by 2 to 7 pi by 6, for this 120 degrees D3 conducts, and next 120 degrees D1 conduct, and next 120 degrees D2 conduct. So that is what can be indicated here in conduction diagram. So T1 would conduct during this 120 degrees, T2 and T3 they are going to conduct in next 120 degrees and 120 degrees respectively. And D3, D1, D2 they are going to be conducting this way, that is from pi by 2 to 7 pi by 6, 7 pi by 6 to 11 pi by 6, 11 pi by 6 to 15 pi by 6 respectively. So D3, D1 and D2 are going to conduct. And one of the important observation here, so in negative group we have only diodes. So and they would conduct independent of alpha. So conduction diagram for diodes are not going to change, that is independent of alpha. But conduction diagram for thyristors, of course they would change. Okay, that would change. For example, alpha is equal to 30 degrees, then what we should do, we should shift this conduction diagram by 30 degrees. If alpha is equal to 90 degrees, then you should shift this conduction diagram by 90 degrees for thyristors only. For diodes, no, there is no change in the conduction diagram. So this is one of the important observation. When it comes to full converter, we have seen the operation of full converter in previous class. Conduction diagram for all thyristors will be shifted if you change alpha value, right? Yeah. So that is the difference between semi-converter and the full converter. And one more important observation, so in full converter case there is a possibility that voltage across load can become negative, but in case of semi converter, whenever voltage across load try to become negative, so this this previewing diode would be forward biased and that would conduct. So load current would be shifted from the other path, other thyristors and diode paths. So this any other path to this new path, that is previewing diode. And this previewing diode would improve the load voltage and current profile and also power factor. So let us see the output voltage wave expression. The expression for output voltage, you can see for alpha is equal to 0, the operation of this converter would be similar to that of the full converter, which is also similar to that of the diode rectifier. Now for first 60 degrees, that is from pi by 2 to pi by 6 to pi by 2, output voltage is VAB, and then next 60 degrees VAC, then VBC, and VCA, VBA, VCA, VCB, and VAB, so on. Now every 60 degrees it is going to repeating. In fact, for alpha is equal to 0 degrees, it would act as the diode rectifier, and it is a 6 pulse converter for alpha is equal to 0. Okay. So in order to sketch the output voltage, one should know VAB, VAC, and VBC respectively. And let me assume that connection, supply connection is star connection. Then line voltage would be √3 times the phase voltage, and line voltage leads phase voltage by 30 degrees. That is what indicated here. And you need to sketch these line voltages, and then you need to indicate the output voltage. Okay, let us see that in next slide. So we know from pi by 6 to pi by 2, output voltage is same as VAB, and VAB is indicated with this dotted line. So let you indicate that the value of output voltage is same as VAB from pi by 6 to pi by 2. Let you indicate that with this kind of thick curve. And same thing would repeat for remaining next 60 degrees and next 60 degrees and so on. It is a 6 pulse converter. Output voltage for 60 degrees you can find out. So from pi by 6 to pi by 2, it is same as VAB, which is equal to VML sin omega t plus pi by 6. Okay. So, and it is 6 pulse converter, you can find out average value. Average value would be very close to the peak value. That is what's shown here. Now, if in case alpha is equal to, let me take alpha ranging from 0 to 60 degrees. So for example, let me take alpha is equal to 30 degrees. If you take alpha is equal to 30 degrees, what would happen? Conduction diagram for thyristors would be shifted from alpha is equal to 0 to alpha is equal to 30. So 30 degrees shift would be there for conduction diagram for thyristors. So now you can see previously thyristor 1 was triggered at this instant, now it is triggered at this instant. Coming to diodes, there is no change in the conduction diagram. Now for alpha is equal to 30, you can see that from omega t from pi by 6 plus alpha to pi by 2, output voltage is same as VAB, and then pi by 2 to 5 pi by 6, it is same as VAC. That is what indicated here. And similar kind of operation would be repeated for next 120 degrees and so on. Now you have the frequency of output voltage 2-3 times of the frequency of supply voltage. Okay, so we have 3. So the output voltage is repeating for every 120 degrees or 2 pi by 3 radians. Okay, so in order to find out average value or RMS value of output voltage or current, one should know mathematical expression for this 120 degrees. So V0 is equal to VAB, that is VML sin omega t plus pi by 6 for omega t ranging from pi by 6 plus alpha to pi by 2, and that is equal to VML, that is equal to VAC, that is same as VML sin omega t minus pi by 6 from pi by 2 to 5 pi by 6 plus alpha. Okay, so frequency of output voltage is 3 times of that of the supply frequency. If you find out average value, yes, average value would be little lower when compared to the previous case, that is from alpha is equal to 0. Now for alpha ranging from 0 to 60 degrees, you can find out the average value of output voltage. Mathematical expression for average value would be this. So you have to integrate the output voltage for 120 degrees or 2 pi by 3 radians. We know from pi by 6 plus alpha to pi by 2, it is same as VML sin omega t plus pi by 6, and pi by 2 to 5 pi by 6 plus alpha, it is VML sin omega t minus pi by 6. So integrate this, find out area under the output voltage and take its mean value. You would get that value is equal to 3 VML by 2 pi into 1 plus cos alpha. So please note this particular expression. Okay, this is one of the important expressions. Please note this. And similarly, output RMS value. So output voltage RMS value, again you have to the formula is our procedure to find out RMS value is square the output voltage and take its mean value and apply the square root. So you do that and you get that value would be equal to VML by 2 into square root 3 upon pi into 2 pi by 3 plus square root 3 upon 2 into 1 plus cos 2 alpha under root or square root. Now similarly, if one want to find out the output current RMS value or average value, so assume that current is ripple free. So average value, RMS value both are equal, that is equal to average value of output voltage minus battery voltage by resistance value. Right? So in previous lectures we have derived this formula. Now for example, if alpha is 60 degrees, so what would happen? If alpha is 60 degrees, then this conduction diagram for thyristor would be 60 by 60 degrees, where conduction diagram for diodes is going to be same as that of alpha is equal to 0. So if you shift that by 60 degrees, then thyristor 1 and D3 are going to conduct simultaneously for 120 degrees. Similarly, T2 D1 and T3 D2, so they are going to conduct simultaneously. Okay, and during this period, that is from pi by 6 plus alpha to 5 by 6 plus alpha, output voltage would be same as VAC. So VAC is this, right? So VAC is this. VAC is going to lag VA by 30 degrees or VAB by 60 degrees. So you sketch that, and its magnitude is equal to root 3 times the phase voltage, assuming that supply is star connected. Now for this case, so let you indicate that the output voltage is same as VAC. Output voltage is same as VAC for this period. So let you indicate that, and so same kind of wave shape would be repeated for remaining cycles also. And if you see, within completion of one cycle of supply voltage, we have 3 cycles completed by the output voltage. It is a 3 pulse converter. Okay, output voltage, we have 3 pulses in one pulse completion of the one cycle completion of the input supply. So it is a 3 pulse converter, and V0 is equal to VML sin omega t minus pi by 6, that is VAC, for pi by 6 plus alpha to 5 pi by 6 plus alpha. So it is a 3 pulse converter. Average value you can find out. So average value would be something like this. Okay, you can find out. You can derive the formula and you can find out. So we will see what is the formula for average value sometime later. Now what happens for alpha is equal to 90 degrees? Let me take alpha is greater than 60 degrees. So you can see at alpha is equal to 60 degrees, the output voltage just becomes 0. Right? You can see at omega t is equal to pi by 6 plus alpha. So you can see that output voltage is touching this 0. Okay, and if you increase alpha more than 60 degrees, then output voltage will try to become negative. But due to presence of freewheeling diode, the output voltage is prevented from becoming negative. So once output voltage slightly become negative, then the diode, freewheeling diode would be forward biased, and current through load would be shifted to freewheeling diode. So output voltage becomes 0 during that freewheeling period. So that is what indicated here. You can see the conduction diagram is shifted. You can see that conduction diagram is shifted by 90 degrees for thyristors, where diodes there is no shifting. So now you can see that for alpha is equal to 90. So from pi by 6 plus alpha to something like maybe 7 pi by 6. I think 7 pi by 6. Okay, let me. Yeah. So for alpha is equal to for omega t ranging from pi by 6 plus alpha to 7 pi by 6 plus alpha, output voltage is same as VAC. And at 7 pi by 6, you can see that output voltage is touching 0 point, and it is trying to becoming negative at this instant. And once it try to become negative, for freewheeling diode would come into conduction mode. So none of the thyristors are going to be none of the thyristors are going to be thyristors or D1, D2, D3. So none of the diodes except freewheeling diode would be in conduction mode. In fact, output current is same as freewheeling diode current, and during that period, and that period is shown with this shaded region in the conduction diagram, and during this period output voltage would be 0. And again, similar kind of wave shape you can see for every 120 degrees. So you have this kind of pattern for output voltage from pi by 6 plus alpha to 7 pi by 6, it is same as VAC, and then 7 pi by 6 to 5 pi by 6 plus alpha, you will have the voltage value would be 0. So this is the mathematical expression for output voltage, and again it is a 3 pulse converter. For alpha greater than 60 degrees, always it is going to be a 3 pulse converter. Coming to average value, yes, you can find average value. Average value is little lower compared to previous cases. As you increase alpha value, average value of output voltage would be decreasing, and if alpha is equal to 180 degrees, then that becomes 0. So one important point to be noted about the semi-converter is that there is no possibility of the average voltage to become negative, because there is no negative portion of the voltage. Due to presence of the freewheeling diode, there is no negative voltage present across the output voltage for any duration. So there is no question of the negative average voltage. So always the semi-converter would be operated in one quadrant, that is corresponding to a rectifier mode of operation. Coming to RMS value and average value, of course you can find out RMS value and average value using this formula for alpha greater than 60 degrees. So we know, once again, you have to find out area under the curve and you have to take its mean value. Again you will get this similar kind of formula, 3 VML by 2 pi into 1 plus cos alpha, where VML is peak value of line to line voltage, alpha is the firing angle. Similarly, RMS value you can find out, that is equal to VML by 2 into square root 3 upon pi into pi minus alpha plus 1 upon 2 sin 2 alpha square root. So that way one can find out the RMS value. Coming to the average and RMS value of the load current, you can use this formula in order to compute average or RMS value of the output current. So average value of output voltage, that is this, minus battery voltage by resistance value, gives you the average value of the load current, which is same as the RMS value for this assumption, that is load current is ripple free. When load current is going to be ripple free, so in case load is highly inductive in nature. So this is the operation of 3-phase semi-converter, and if you have any doubts, so please reach me through the mail ID that is given in the description. Thank you.